Quantum mechanics examples. Free particle position space probability density of a Gaussian wave packet moving in one dimension in free space. The simplest example of quantum system with a position degree of freedom is a free particle in a single spatial dimension. A free particle is one which is not subject to external influences, so that its Hamiltonian consists only of its kinetic energy. H is equal to 1 by 2 mp square or equal to minus h cut square by 2m partial square by partial x square. The general solution of the Schrödinger equation is given by psi x, t equals 1 by under the root 2 pi integral from minus infinity to infinity psi steric k 0 exponential iota k x minutes h cut k square by 2mt into dk, which is a superposition of all possibly plane waves. Exponential iota k x minutes h cut k square by 2mt into dk, which are eigenstates of the momentum operator with momentum p equals h cut k. The coefficients of the superposition are psi asterisk k, 0, which is the Fourier transform of the initial quantum state psi asterisk x, 0. It is not possible for the solution to be a single momentum eigenstate, or a single position eigenstate, as these are not normalizable quantum states. Instead, we can consider a Gaussian wave packet psi x, 0 equals 1 by 4 under the root pi alpha exponential minus x square by 2 alpha, which has Fourier transform, and therefore momentum distribution. Psi asterisk k, 0 equals 4 under the root alpha by pi exponential minus alpha kappa square by 2 ec. That is, we make alpha smaller, the spread in position gets smaller, but the spread in momentum gets larger. Conversely, by making alpha larger we make the spread in momentum smaller, but the spread in position gets larger. This illustrates the uncertainty principle. As we let the Gaussian wave packet evolve in time, we see that its center moves through space at a constant velocity, like a classical particle with no forces acting on it. However, the wave packet will also spread out as time progresses, which means that the position becomes more and more uncertain. The uncertainty in momentum, however, stays constant. In a box, one-dimensional potential energy box or infinite potential well. Well, the particle in a one-dimensional potential energy box is the most mathematically simple example where restraints lead to the quantization of energy levels. The box is defined as having zero potential energy everywhere inside a certain region, and therefore infinite potential energy everywhere outside that region for the one-dimensional case in the x direction. The time-independent Schrödinger equation may be written minus h cut square by 2m partial square psi by partial x square equal to energy psi. Differential operator defined momentum into x is equal to minus iota h cut partial by partial x. The previous equation is evocative of the classic kinetic energy analog. 1 by 2m momentum square is equal to energy with state psi, in this case having energy E coincident with the kinetic energy of the particle. The general solutions of the Schrödinger equation for the particle in a box are psi x is equal to a exponential iota kx plus b exponential minus iota k xor. From Euler's formula, psi x is equal to c sin x plus d cos kx. The infinite potential walls of the box determine the values of c, d and k at x is equal to 0 and x is equal to L, where psi must be 0. Thus at x is equal to 0, thus psi 0 is equal to 0 c sin plus d cos 0 is equal to d, and is equal to 0 at x is equal to L. Psi L is equal to 0 is equal to c sin kl, in which c cannot be 0, as this would conflict with the postulate that psi has norm 1. Therefore, since sin kl equals 0, kl must be an integer multiple of pi k equals n pi by l n equals 1, 2, 3, up to so on. This constraint on k implies a constraint on the energy levels, yielding En is equal to h cut square pi square n square by 2m L square, or equal to n square h square by 8m L square. A finite potential well is the generalization of the infinite potential well problem to potential wells having finite depth. The finite potential well problem is mathematically more complicated than the infinite particle in a box problem, as the wave function is not pinned to 0 at the walls of the well. Instead, the wave function must satisfy more complicated mathematical boundary conditions, as it is non-zero in regions outside the well. Another related problem is that of the rectangular potential barrier, which furnishes a model for the quantum tunneling effect that plays an important role in the performance of modern technologies such as flash memory and scanning tunneling microscopy. Harmonic oscillator. Some trajectories of a harmonic oscillator, i.e. a ball attached to a spring, in classical mechanics AB, and quantum mechanics CH. In quantum mechanics, the position of the ball is represented by a wave, called the wave function, with the real part shown in blue and the imaginary part shown in red. Some of the trajectories, such as c, d, e, and f, are standing waves, or stationary states. Each standing wave frequency is proportional to a possible energy level of the oscillator. This energy quantization does not occur in classical physics, where the oscillator can have any energy. As in the classical case, the potential for the quantum harmonic oscillator is given by verses into x is equal to 1 by 2 m omega square x square. This problem can either be treated by directly solving the Schrödinger equation, which is not trivial, or by using the more elegant latter method, first proposed by Paul Dirac. The eigenstates are given by psi n into x is equal to under the root 1 by 2 power n factorial dot into m omega pi h cut power 1 by 4. Dot exponential power minus m omega x square by 2 h cut into dot hn. Into under the root m omega by h cut into xn equals 0, 1, 2 up to so on. Where hn are the Hermite polynomials hn into x is equal minus 1 power n exponential x square partial n by partial xn into exponential minus x square. And the corresponding energy levels are En is equal to h cut omega into n plus 1 by 2. This is another example illustrating the discretization of energy for bound states. Mach-Zehnder interferometer. The Mach-Zehnder interferometer (MZI) illustrates the concepts of superposition and interference with linear algebra in dimension 2, rather than differential equations. It can be seen as a simplified version of the double-slit experiment, but it is of interest in its own right, for example in the delayed choice quantum eraser, the ELITZURBAIDMAN bomb tester, and in studies of quantum entanglement. We can model a photon going through the interferometer by considering that at each point it can be in a superposition of only two paths. The lower path, which starts from the left, goes straight through both beam splitters, and ends at the top, and the upper path, which starts from the bottom, goes straight through both beam splitters, and ends at the right. The quantum state of the photon is therefore a vector psi element of c squared that is a superposition of the lower path psi l equals 1 0 and the upper path psi u equals 0 1, that is, psi equals alpha psi l plus beta psi u for complex alpha, beta. In order to respect the postulate that psi equals 1, we require that alpha squared plus beta squared equals 1. Both beam splitters are modeled as the unitary matrix B equals 1 by under the root 2 matrix 1 iota iota 1, which means that when a photon meets the beam splitter it will either stay on the same path with a probability amplitude of 1 square root 2, or be reflected to the other path with a probability amplitude of iota square root 2. The phase shifter on the upper arm is modeled as the unitary matrix P equals matrix 1 0 0 exponential delta phi, which means that if the photon is on the upper path it will gain a relative phase of delta phi and it will stay unchanged if it is in the lower path. A photon that enters the interferometer from the left will then be acted upon with a beam splitter B, a phase shifter P, and another beam splitter B, and so end up in the state BPB psi L equals iota exponential iota delta phi by 2 into minus sin delta phi by 2 and plus cos delta phi by 2, and the probabilities that it will be detected at the right or at the top are given respectively by P upper is equal to psi upper BPB psi lower absolute whole square or equal to cos square delta phi by 2, and P lower is equal to psi lower BPB psi lower absolute whole square or equal to sine square delta phi by 2. We use the Mach-Zehnder interferometer to estimate the phase shift by estimating these probabilities. It is interesting to consider what would happen if the photon were definitely in either the lower or upper paths between the beam splitters. This can be accomplished by blocking one of the paths, or equivalently by removing the first beam splitter, and feeding the photon from the left or the bottom, as desired. In both cases there will be no interference between the paths anymore, and the probabilities are given by P upper equals P lower equals 1/2, independently of the phase beat. From this we can conclude that the photon does not take one path or another after the first beam splitter, but rather that it is in a genuine quantum superposition of the two paths.